For power and efficiency, there's a couple things we need to kind of look through here. Let's start with efficiency. It's actually section 5.1, I think, in your textbook. But for efficiency, it's the ratio of useful work to the energy input. And there's a couple different ways that we can write this. So sometimes you will see useful work divided by work input, where remember work and change in energy are kind of the same thing. So sometimes you'll see it like this, useful work over work input times 100%. Sometimes you'll see it like this, percent efficiency is energy output over energy input. Sometimes you'll see like useful work over energy input or something like that, or useful energy output over energy input, any combination of stuff like that. Basically what we're trying to say is it's the useful energy divided by whatever you put into it. So you put a bunch of energy into a machine. The machine only does some stuff that's useful. The rest of the energy is kind of wasted. Things like heat and sound are common things that a machine sort of makes, or a way that it uses energy, even though that's not very useful to us. Let me give you an example. Let's say you've got an old-fashioned light bulb. Okay, so you've got this old-fashioned light bulb, if you know what I mean, an incandescent light bulb. This kind of a light bulb, if you can picture it, it kind of has these little ding, this kind of light bulb. And you turn on this incandescent light bulb. We don't really sell these anymore in Ontario. For the most part, you can buy some, but most bulbs now are maybe fluorescent, but even that's kind of getting old. Most lights now are LEDs. LEDs are way more efficient. Let's see how efficient, though, an incandescent light bulb is. So typically an incandescent light bulb gives off, you put 100 joules of electrical energy to run this light bulb. 98 joules are given off as heat, and the rest is given off as visible light. Find the percent efficiency. Okay, so we just kind of finished saying percent efficiency is it's the useful output. I'm going to say useful output energy. So useful E out divided by whatever energy you put in. And then times 100%. That's just to make it a percent. Okay, so in this case, our useful energy output is not this 98 joules given off as heat. That's not the useful purpose of a light bulb, unless you're using like an easy bake oven or something like that. But the purpose of the light bulb is to give off visible light that you can see by. Okay, so the useful energy output is, if you put 100 in and 98 are given off as heat, the rest of it, 2 joules, is given out as useful visible light energy. Divide by 100 and then times 100%. What we're going to get out of this thing, percent efficiency, is 2%. Okay, so you could say 2.0 or something, 2% efficient. This light bulb, this incandescent style of light bulb, is wildly inefficient. That's why they're for the most part in many jurisdictions, like in Ontario, province of Ontario, they've kind of outlawed selling these, other than for some very specific purposes. So in your oven, you might still have an incandescent light bulb because it's got to withstand the heat of the oven. But most places now only are selling LED light bulbs. They save you money, which is when you're running them, which is a good thing. They also save the province a whole lot of electricity because for efficiencies, this is a terrible efficiency. Just kind of as a comparison, LED light bulbs tend to be more like 90-95% efficient. And you know from getting test marks that that's a good mark. So you want those more efficient light bulbs. Quick tip in here. Let's see if I can give you a little bit of visibility there. Percent efficiency, there's different ways to write the equation, but you can often think of it as useful work out over useful work in. And where work out, that output work, you can think of it as how did the object's energy change. So this is tough with our light bulb example, but if you're talking about like a car going up a hill or something like that, if you want to know what useful work was done, it's often what was the change in energy. Whereas the work input is often this FD cos theta. So if you ever see work out over work in, it's often going to be like, what was the change in energy up here? And what was the FD cos theta down here? That's not always true, but that's a good kind of rule of thumb. Sometimes we have to try to figure out what's the useful work and what versus what was the input work. And so that can be something that can help you with those questions. Power, this is actually section 5.2 in our textbook. Power is the rate at which work is done. Or you could say the rate at which energy used. Remember, work being done is the same as energy being used. As an equation, we'll see it either way. So sometimes you'll see work on top up here. Sometimes you'll see energy or change in energy on top over here. Ah, yes. Here's a little joke. You're a unit of power, Harry. I'm a watt. Remember, hopefully you remember, or maybe you've never heard this before, but power is measured in watts. So just like our good friend Harry Potter says over here, power measured in watts, that's this thing over here. And don't confuse that W with this W. That is work. So if you see it in an equation, it's a variable. That's kind of going down this thing. If you see a W in the equation, that is work. If you see a W behind a number, that is a unit. Whoop. That's a number like this thing here. That's watts. That's the unit. Time measured in seconds in general, for our purposes anyways, that's going to be true. And energy is measured in joules, work measured in joules as well. Power is measured in watts. Oh yeah, 1 watt is 1 joule per second. So you can kind of see, for example, up here, energy is measured in joules, but time is measured in seconds. Okay, so this joules per second that you've got over on this side, that's going to be the same as a watt over on this side. So 1 watt is 1 joule per second. Here's another little joke for us. You're a wizard, Harry. You're a hairy wizard. Huh? Huh? All right, enough of that. Let's do a real example here, you guys. Mr. G lifts a 10-kilogram bag of flour straight up to put it in his shopping cart. If he lifts it 1.5 meters up in 2.0 seconds, find his power. You can kind of picture, I don't know, here's like a shopping cart or something. They kind of look something like this. And the bag of flour starts down here on the ground, and it gets lifted up and put into here. And let's see, what's the number? 1.5 meters. We'll say that this thing is 1.5. I don't know if that's a realistic number, but let's just say 1.5 meters. Maybe it's the top shelf or something, one of those higher shelved ones. What we know is the mass that I'm lifting, 10 kilograms. He lifts it up a distance or a change in height, you could say, of 1.5 meters. The time it takes is 2.0 seconds. Okay, so we know power is work over time, or I'm going to use in this case, change in energy over time. The type of energy that I'm giving to this bag of flour, let's assume it starts at rest and it ends at rest up here. There's no change in kinetic energy. This is a change in gravitational potential energy. So we know change in gravitational potential energy is mgh2 minus mgh1 over time. And you could write that, I'll kind of say over here, you could write that as mg delta h over time. That's also fine, okay? So you could say that. That's kind of a simplified version. I'm going to write it sort of this way. Over here, I'll use this version of it. The delta H thing that we're subbing in, you could sub that guy in over here. We'll get the same answer. What I'm going to say, though, is height 1. Let me choose one other color here. I'm going to say height 1 down here on the ground is 0. But height 2, when it's up here in the shopping cart, that is 1.5 meters. Okay, so when I go ahead and sub into this thing, power, mass is 10, G is 9.8, height 2 is 1.5 meters, minus, if height 1 is 0, this whole thing here goes away, so just minus 0 on the top. The time this thing takes is 2 seconds. We'll multiply this stuff out. What have we got? 10 times 9.8 times 1.5. 147 divide by 2, 73.5. Power, it's approximately 74 watts for our sig digs. Remember, for sig digs, 2 sig digs, 2 sig digs, we'll always take this as 2 sig digs up here. Pretend there's a decimal at the end. Oh yeah, one other equation. This one doesn't come up super often, but every once in a while this one will come up. Um, Power is also force times average velocity. Okay, that's one. We may see that a little bit in class. Doesn't come up too often. Something else to note, this question comes up, or this conversion, I guess, comes up every once in a while. 746 watts is 1 horsepower. So if you're wondering, like, you might hear this for light bulbs, power is 1 watt or 50 watts, or your computer's power supply, right, is 100 watts or 75 watts or something like that. But for cars, we always talk about horsepower. It's a weird, archaic old unit. I don't know why we still use it. It's just because it's been around for a long time. Anyway, 746 watts is 1 horsepower. And we won't be running tomorrow probably, but anyways, there's some questions for you guys to try.